Quadratic equation is perhaps the most well-known concept from algebra. If you think you know everything about it, let me try to surprise you. We want to solve a slightly odd and vague problem. Given a polynomial x squared plus bx plus c, let x1 and x2 be its roots. What is the probability of these roots being real? If you feel like this question does not make sense, you are right. But making sense of it is a mathematical exercise in itself. So what does probability mean in this case? Well, only these coefficients b and c influence the roots, right? So we're choosing b and c from all real numbers, of which there is infinity. Sometimes they produce a polynomial with complex roots, and sometimes with real roots. Can you see a problem here? Of course, infinity is the troublemaker here, because when we say that b and c are random real numbers, we're not being rigorous. Probability has a strict definition in mathematics, and an important part of that definition is normalization. In simple terms, it requires that the sum of probabilities of all possible values of a random variable equates to 1. And probability is given by a probability distribution, and we said nothing about it so far. So what we don't have in our problem statement is what distribution b and c are taken from. So we need to work it out ourselves. Intuitively, we know that every possible real number must have an equal chance of becoming either of our coefficients. But if this chance is non-zero, the total probability becomes an infinite sum of constant positive values, which becomes unbounded. At this point, you may say that the question is incorrect and does not have a solution, and you won't be wrong. But it will also be a total buzzkill. Let us try to answer this question as best as we can while maintaining full mathematical rigor. You probably notice how x squared does not have a coefficient, which I do for simplicity, and we will find it useful later. So when does it have real roots and when does it not? Obviously, it is influenced by the value of the discriminant. When b squared is more than or equal to 4c, the roots are real. This condition defines a parabola centered at the origin, and the inequality is essentially this area here. So we want to divide this area by the entire area of the plane, which we are not allowed to do because of infinity, as we saw before. But what is the best thing that we can do? Well, we can restrict the domain down to a bounded symmetric shape, a square. As a side quest, can you explain why only this shape is right to consider? Anyway, it is clear that the red shaded area corresponds to all cases when the roots become complex. It is an easy calculus exercise to find it. The probability of having complex roots is then given by this value. Interesting. As L, the radius of our domain, goes to infinity, this value tends to 0. So the probability of having real roots tends to 1. Isn't it exciting considering that polynomials achieve algebraic closure over complex numbers? But what happens when we consider the most general case, where x squared also has a random coefficient? You can extrapolate that instead of having a square region, we will have a cubic one. I suggest you finish calculations yourself and share your response in the comments below.